In the second part of thermochemistry, we talk about calorimetry and the heats of reaction. And the heats of reaction, there are two things we'll talk about. One is Hess's law, and the other one is heats of formation. So first of all, heat capacity. Heat capacity is the amount of energy that is needed to raise the temperature of a sample by 1 degree Celsius or Kelvin. Now remember, Celsius and Kelvin, they are the same scale. We can't use the same for Fahrenheit, okay? They work on a little bit of a different scale. So heat capacity is actually quantifiable, okay, which means it is an amount, all right? So that's why there is a formula for this. So Q, which is the heat, that's the amount of heat, and then C is the heat capacity, and then this would be the change in the temperature, which for heat capacity would be 1 degree Celsius or Kelvin. Hopefully you've noted that in all of these calculations we are using degree Celsius. We don't have to convert anything to Kelvin, so we can work on that even here. Okay, so delta T would be given in Celsius. If you were looking for molar heat capacity, then of course it would be heat capacity of 1 mole of substance, that's all. So heat capacity does not include the amount of substance, whereas in the molar heat capacity, it would be 1 mole of substance. And then there is something called the specific heat capacity. And in the specific heat capacity, it's 1 gram of substance. So again, remember, with 1 mole of substance is really great when you're trying to compare moles to moles. But if you're working in grams, then you can work with specific heat capacity. Now, most of the time for us, we will be working with specific heat capacity and sometimes with the heat capacity as well, because the heat capacity and specific heat capacity, the only thing that is different between the two is the mass, okay? But otherwise, it's the same thing. The C here has to do with the heat capacity. The S here has to do with the specific heat capacity. That's all, which means S is a little bit more specific than C, all right? But otherwise, delta T, that's the change in temperature, Q is the heat, okay, in there. So that's the only thing, the mass is the only thing that is different between heat capacity and specific heat capacity. Okay, so how do we actually measure these heat capacities? We actually do them in a calorimeter, all right? And so this is what a calorimeter would look like. This is how it would look like in a lab. So we generally tend to use styrofoam cups because they are very good insulators. So whatever heat that you generate during the reaction inside the styrofoam cups calorimeter, it would be very well recorded. Okay, so you can measure the temperature changes even up to 0.5 degrees Celsius in styrofoam cups. In a lab, in a more specific environment, you would be working in a very nice isolated system like this, where everything is completely insulated. The bomb calorimeter has water around it, so when you burn the substance inside it, the heat is transferred to the water. So it requires a little bit more calculation, as in the first one you would do is calculate the amount of energy required to raise the heat of water, raise the temperature of water, and then you'll find the specific heat capacity. So it's just a little bit detailed calculation, but otherwise it works great. Of course, it works great. So this is really the best way to find out the heat capacity of, say, things like food. Okay, so it's one of the best things to do. Here are some values for specific heat capacity, just for your information. Usually this will be given to you in case you're doing any exam questions or anything like that, and you're most welcome to refer to the table, of course. You're not required to memorize any of this. So aluminum, for example, the specific heat is 0.900 joules per gram per degree Celsius, okay, which means it takes 0.9 joules to raise the temperature by 1 degree Celsius of 1 gram of aluminum, okay, which means it does not take a lot of energy compared to, say, let's go down to ethanol. Okay, ethanol, it takes 2.46 joules to raise the temperature, and then for water it takes 4.184 joules to raise the temperature by 1 degree Celsius of 1 gram of water. So which means that water has a very high specific heat, whereas aluminum has very low. And the lowest one here actually is for mercury. Okay, I mean, you really don't need much energy to start heating mercury up, which is why mercury makes for a really good chemical in the thermometer. Also, of course, it's a liquid, but otherwise also it changes very quickly. Okay, the heat capacity is so low that it really registers heat very well. So you use the specific heat to figure out the function of whatever you want to use. Okay, so what are you going to use aluminum for? You can use aluminum for cookware because you want things to heat up quickly. You can use water as a coolant because it can absorb so much heat that you will need a lot of it in order for it to get hot. Okay, and so you use the specific heat in order to figure out which kind of metal to use where, or what kind of substance to use where. So in the following few slides, I have some examples for you, some solved examples. Calorimetry is a very simple experiment per se, because all you have to do is take a substance and burn it in a calorimeter and then measure the heat. So the best thing to do for calorimeter is, of course, just to go through some worked problems and see how to use the specific heat calculation. All right, so let's go through this one first. A piece of zinc weighing 35.8 grams was heated. So the temperature change here is about 8 degrees, and how much heat was required? That's the question. And the specific heat is given. This is a very, very simple, straightforward question. All you have to do is plug everything in the formula and come up with the answer. Okay, so if the specific heat is given to us, then it means you're going to use a specific heat formula, which is Q is equal to MST. And the delta T turns out to be the final temperature minus the initial, which is 8 degrees Celsius. And so then Q becomes 35.8, which is the mass given of zinc, and then the specific heat of zinc that is given to us and multiplied by the temperature change. So it's a very simple, straightforward calculation. There is not much to it. Make sure you cancel out all your units, okay, to make sure that you're remaining finally with the joules over here. Okay, so specific heat calculations, if all the data is given to you, then they're very straightforward calculations. Sometimes in calorimetry, the harder ones are when you have to actually transfer heats, okay, which we're going to do in a minute. Okay. So here's another example. Okay, here is nitromethane, an organic solvent, burns in oxygen according to the following equation. And then so the mass of the nitromethane is given to you. You place 1.724 grams of nitromethane in a calorimeter with oxygen and ignite it. Okay, the temperature of the calorimeter increases um, from this to this, 22.23 to 28.81. The heat capacity of the calorimeter is given also. Write the thermochemical equation for this. Okay, so we're not really worried about the heat capacity of nitromethane over here. Okay, that's not what the question is. The heat capacity of the calorimeter is actually given to us. Okay, which means the specific heat is not the one that we're going to use, which means that Q reaction is equal to minus C cal delta T. That's the one we're going to use. The C cal here is actually the specific heat of the calorimeter. Now, when you use bomb calorimeters, like the one that I showed you the picture of before, where everything is in a closed system, then the calorimeter itself sometimes may also absorb a little amount of energy. So you have to know the specific heat of your calorimeter, and that is actually what this is. And that's the number that's given to us here. The heat capacity of the calorimeter is this. It can be a very small number, also it can be a large number, but it has to be accounted for, okay, in some cases, so that you can get an accurate answer. So anyhow, so that's what the question is really about. It's not about specific heat at all, okay? It's just about writing the thermochemical equation, which means that you're just finding out what the heat of reaction is going to be. So the Q reaction, the heat of the reaction is equal to minus C cal. And why is it minus? Minus because you're burning nitromethane. So if you're burning the nitromethane, it means that it's going to be an exothermic reaction. So you can make some of these normal judgments yourself and say, okay, if I'm giving off energy, it's going to be a negative, okay, because that's exothermic reaction. So then the calorimeter here is going to be, this is the specific heat for it, the change in the temperature, 28.81 minus 22.23. So that means this is the kilojoules that was actually evolved during the reaction. So now what you have to do is to find out how much heat was involved per mole, because when you're asked for a thermochemical equation, in thermochemical equations, you have to write everything per mole. Okay, and so in that case, you have to find per mole of anything. So here in this case, okay, this is 1 mole of nitromethane. Okay, so in case of 1 mole of nitromethane, you have 61.04 grams of nitromethane. So what you will do is then you will take this kilojoules, and this amount of energy was given off by 1.724 grams of nitromethane. Okay, that's what the amount was given over here. So if 1.724 grams gave off that much, then you have to find out how much was given off if you were using 1 mole, which is then 61.054 grams of nitromethane. And that would be minus 709 kilojoules. Okay, so that is how you will write this equation. So you'll just write this equation and then write this. Now, when you write the minus 709 here, we're just writing kilojoules. Remember, it is kind of understood that this is going to be per mole, so you don't have to write per mole. So it's kind of one of those taken for granted things. Another example. A metal pellet, 85 grams, at an original temperature of 92.5 degrees Celsius is dropped into a calorimeter with 150 grams of water at an original temperature of 23.1 degrees Celsius. The final temperature of the water in the pellet is 26.8. Okay, so calculate the heat capacity and the specific heat, okay, for the metal. So now in this case, we have to calculate both the heat capacity as well as the specific heat for the metal, okay. And so since we are calculating that, and let's see, what else are we given here? We're given the mass, we're given the mass of the water, and then we are given, of course, the temperature, okay, of the pellet. Okay, so that's what we're given over here. So the first thing we are going to do is we're going to find out the amount of energy that was released in the water, okay, because the pellet was dropped in the water, all right? So if the pellet was dropped in the water, then what is the energy changes going on in the water? Okay, that's the first thing you will find out. So that's how we start this. So ms delta T, and the mass of the water is 150. The specific heat of water is this, which is you can get from the data table, 4.184. And the change in the temperature for the water is 26.8 minus 23.1 degrees Celsius, which is 3.1 then. Okay, so that is the amount of energy that is gained by the water when the metal pellet was dropped into the water. So this is the amount of energy that is gained, okay, which means that the reverse sign would be how much the energy was released by the pellet. Okay, so if this is the amount of energy that was gained, it must be the equal energy that was lost by the pellet. Okay, so now we're going to go ahead and calculate the heat capacity of the pellet, because now that we know how much energy change has occurred from dropping the pellet in the water, now we have to look at the change in the temperature from the water and the pellet. Okay, so heat capacity is given by Q is equal to C delta T, and remember, C is the heat capacity, Q is the amount of energy. The Q is what we just calculated over here, C is what we are calculating for, delta T is the change in the temperature. Okay, and the change in the temperature then would be minus 67.7 degrees Celsius, because it is going to be 92.5, which is the initial temperature of the pellet, and then subtract 26.8, okay, which is the final temperature of the water. So initial minus final, or final minus initial, excuse me, that's why there's a minus. So final minus initial, so final was 26.8, initial was 92.5, and that gives us the minus 65.7 degrees Celsius. Okay, and so that is equal to 35 joules per degree Celsius. Remember, this is also minus over here, the minus 2300, because this was the amount of energy released. Okay, so you cancel out the minuses also, okay, the minus signs. So you ended up with 35 joules per degree Celsius. That is the heat capacity of the pellet. To find the specific heat capacity of the pellet, you have to divide it by the mass. Okay, that's all you have to do. So that will give you the heat capacity per gram, and that is specific heat. Okay, so one last thing to do, and then that's how you know the specific heat. So in this calculation, you can see that there was one additional thing we had to do, which is that you need to find out how much energy was transferred into the water. Once you know how much energy was transferred into the water, that is the energy you're going to use to calculate the heat capacity of the pellet. One last thing, okay, about this calculation is we could have calculated the specific heat directly, okay, from here. Once we had known what the energy transfer was, we could have used the specific heat formula, okay, over here. But the thing was that we were asked for the heat capacity of the pellet also. That's why we used this formula first. If not, we would have used this formula right away, and to calculate the S, it would have been Q divided by M delta T, which is exactly what we did over here. We divided by mass over here, and delta T is right here. So that's what we did with the amount of energy released that we calculated before. Okay, so because we were supposed to calculate the heat capacity, this became a two-step process. But if we were calculating specific heat, we could have just used this formula also directly, okay, and skip this step. So make sure you read the question carefully and see what is being asked of you, whether it's heat capacity or specific heat, okay, of anything, because in heat capacity, you don't need the mass. All right, next example. A snack chip with a mass of 12.336 grams was burned in a bomb calorimeter. The heat capacity of the calorimeter is 38.57 kilojoules per degree Celsius. During the combustion, the water temperature rose by 27. Calculate the energy, okay, for the chip. Now, this energy is kilojoules per gram, okay? So we don't have to do heat capacities over here. We're calculating the energy of the chip. Hopefully, with all of these different examples, you have an idea of every single type of calculation that we can do with calorimeter. All right, so again, we go for Q reaction. Why are we going for Q reaction? Because we're not doing the mass right now, okay? We'll do the mass when we get to calculating the energy, okay, which is going to be in kilojoules per grams. That's when we're going to use the mass. So right now, we're just calculating how much energy was given off. So here again, we are going to use the same formula, which is the C cal delta T. And so the C cal, this is the heat capacity of the calorimeter, which is 38.57. Delta T is given to us, which is 2.7 degrees Celsius. That's the amount of temperature change. Multiply both of them and you end up getting this. And again, the sign here is going to be minus because it is an exothermic reaction. Yes, you're burning something. However, the energy content, okay, of any kind of a food is going to be positive. When you burn it, it's exothermic, but the content itself is a positive quantity. So then you reverse the sign, okay, for it. So now it is 104 kilojoules. And now you can find out also about per gram, how much energy is given off per gram. And that grams is 2.36 over here. So you take that 104 kilojoules divided by 2.36 grams, and you get 44.1 kilojoules per gram. If you were asked to do one more step when you're supposed to calculate calories, then you would just convert the joules to calories, which is then this. And remember, since we talk about food calories, which is a capital CAL, well, capital C, small al, then you have to do one more little calculation, okay? Because food calories are also 1,000, don't forget, okay? 1,000 small c calories. But anyhow, this question was not asked. I just kind of threw it in there. Okay, in case you were asked to calculate in food calories, this is what you would do. Your question was to calculate the energy in kilojoules per gram. So we would have ended it right here. Okay, this would be our final answer. So that's how you would do calculations for calorimeter. We'll do some more examples in class also. Hopefully that will help you adjust to some of the things that you will do in the lab also. Now let's look at Hess's law, and Hess's law is very interesting to work with. It goes to the fact that you can use the enthalpies of different reactions to find out the enthalpy of a reaction that you want. So even if the reaction is not given to you, you can use a whole different set of reactions to figure the enthalpy of a reaction that you need, okay? And so it's just really quite interesting to work with, okay, and quite fun to work with because it's like a puzzle. But in any case, some of the times that we use Hess's law is when you can't figure out the heat of reaction directly, which means in a bomb calorimeter, for example. So in that case, you would need to use Hess's law. So what we do is that, we manipulate a whole bunch of equations that are given to us, or you can actually find those equations in data tables because you may have the heat of reaction of several reactions. So you figure out from the data tables what are the equations that you need, and then you can work the reaction out. Now, remember the reason that we can actually do this, okay, why we can manipulate all of these equations is because delta H is a state function. We talked about this before, and state function means that you have the delta H at a particular place like point A and you are supposed to go to point B, then you can go to point B anyhow you want. It doesn't matter, okay? But the difference between the two is going to be the same, all right? And that is the state function. And it's the property of the state function that you can go anyhow you want, all right? But the delta H is going to be the same for both, which means the difference in the enthalpy is going to be the same. So once you figured out your equations and you manipulated them, and manipulation means that whether you need to inverse a reaction or multiply it by 2, divide it by 2, divide it by 3, or whatever you need to do, you do those kind of things. And remember that as you are multiplying your reaction by 2, you also multiply the delta H by 2. So those kind of things, that's what we call manipulations. And after all that is done, then you add the delta H values. And once you add all of the equations, then you should be finally left with the equation that you are looking for. Okay, and so it's really quite fun to work with. So let's take an example. Okay, over here, if we have graphite and you add oxygen to it and you get carbon monoxide. So what is the delta H for this reaction? Now, I don't think that you really need a Hess's law to do this. You can probably do this in a bomb calorimeter, but since we're sitting in a class, we don't have a bomb calorimeter, all right? So we will do this by Hess's law, all right? So then there are a couple reactions given to you. One is this, where graphite is added to oxygen to give carbon dioxide. The delta H for this is given to us, and the other reaction that is given to us is carbon dioxide to give carbon monoxide and oxygen. So these two reactions are given to us, and we are supposed to figure out the delta H for graphite to give carbon monoxide with oxygen. So when you look at these two reactions, okay, you have to see, okay, where are my reactants, where are my products, am I going to have to reverse the equation, what am I going to have to do? So for example, you look at the first equation. Graphite here is on the left hand side, which is really what you want in your equation also, okay, in your final equation. However, in your final equation that you need, you have 2 moles of graphite, but here we have only 1 mole of graphite. So what you're going to have to do is you're going to have to multiply this equation by 2 in order to get 2 graphite. But remember, when you multiply this equation by 2, you are multiplying the carbon, the oxygen, the carbon dioxide, and the delta H value, okay, by 2. Everything you're multiplying by 2. Then you look at the second equation and you say, okay, let me see what we have here. We have carbon dioxide, you have carbon monoxide, and oxygen. Carbon monoxide is supposed to be on the right hand side, so that is fine. Okay, no problem there. The other thing you have to note here is that we have oxygen on the left hand side as well as on the right hand side. Okay, remember here is the arrow. So on the first equation, it was the reactant, but in this equation, it is actually a product. So when we add these two equations up, we should be left with oxygen only on the left-hand side and not in the product side. And here in the first equation, we also have carbon dioxide. And in the second equation, we also have carbon dioxide. In our final equation, we have no carbon dioxide. So by the time we are done manipulating our equations, we should not have any carbon dioxide left over. Okay? So, all right, when we are looking at this equation, we see that we don't have to do anything to this equation because we need 2 moles of carbon monoxide in the product. And here we have 2 moles of carbon monoxide in our product. So we leave this equation as is, okay, no problems, which means that this number also stays the same. Now the next thing to do is you add up these two equations, and I don't think I have the addition here for you. However, you can see that when we add these two equations up, the graphite will stay because that doesn't get crossed out. We have 2 oxygens over here because we multiplied this by 2. So if you have 2 oxygens here and 1 oxygen over here, by the time you subtract these 2, you'll be left with 1 mole of oxygen, which is what we need here. The carbon dioxide here was 2 moles of carbon dioxide because we multiplied it by 2. So the 2 carbon dioxide there and here will cross out, and then we are left with 2 moles of carbon monoxide as our product. Okay, and I hope you can do all of that. And then in order to get our final delta H, what you will have to do then is add the two heats of reactions that we just figured out. So minus 393 times 2, it will give you 787. And then this one we are not leaving as is, we're not changing that. So by the time you add these two numbers together, you should have 1353 kilojoules, okay, for this particular reaction that you were looking for. So again, if we had been given any other reaction, then we may have had to manipulate that also, okay, in order to find out the delta H for our given reaction. So this is really basically Hess's law. So here's another example for Hess's law. And here are three equations that are given to us. Okay, and we are asked to calculate the delta H for this particular equation. Now, the thing about the equations that are given to us and the equation that we have or that we are calculating for, we should be able to find all of these in these equations. Okay, all the reactants and products. So for example, the borate, the H3BO3, yes, we do have it, okay, over here. B2O3, do we have it? Yes, we do, okay, over here. And then water, yes, do we have water? We have plenty of water. Here, these are the products, and then here is the reactant. So as we are trying to work this reaction and we are trying to figure out what to do with everything, then we'll see what gets crossed out, what gets remaining. Do we have to multiply anything by 2 or 3 or whatever? And then see all of this. We have H2B4O7, which we don't need, okay, because that's not part of our final equation. So eventually we will see that that should cross out, okay, without any problems. The same thing goes for HbO2. The HbO2 is here, and we also have HbO2 over here. So these are both in the product side. So hopefully by the time we do the manipulation, everything should cross out and we should be remaining with the equation that we need, okay, for the delta H. So let's take it one at a time. We have the H3BO3, which is over here in the first equation, okay, but in our final equation we need 2 moles of this. So then we'll go ahead and take the H3BO3 equation, the first one, and multiply it by 2, okay. So once we multiply it by 2, this is the equation we get, okay. And remember, you have to multiply the delta H also by 2. So this is what you end up getting. For the second equation, where we have HbO2, now remember, HbO2 is not part of a product and neither is this. However, we do have water, okay, as part of a product. So which means that what we can do is we can reverse this and we can divide it by 2. Okay, so in that case, we will have 2 HbO2 over here. Now remember, we multiplied the first equation by 2 in order to get 2 moles of H3BO3, which means we also have 2 moles of HbO2. So which means that if we actually divide this by 2, we will actually have 2 HbO2, so we should be able to cancel this out. And if we reverse it, then we'll also be able to cancel it out, okay, because in the first equation HbO2 is on the right hand side, and once we inverse the second equation, it's going to be on the left hand side, okay. So we reverse it and then we divide it by 2, and this is the final equation that we end up getting. So HbO2, which was over here, now we'll have 2 moles of that. And then our products are going to be these two, but now it's going to be half of this and half of the water, okay. And so remember, in all of these thermochemical equations, you're allowed to use fractions, okay. And so go ahead and use halves over here. Then if we are inversing the delta H, then first of all you inverse the sign, which it becomes endothermic now, and then you divide it by 2. So that's our final value for delta H, okay. So that was our second equation. The third equation we have to manipulate, because yes, we still need the B2O3, and we also need the water, okay, not to forget that. And remember, here is the H2B4O7, which is also in this equation, which we need to get rid of, okay. But we need only 1 mole of B2O3, so we're going to divide this equation by 2, okay, and that's how we get only 1 mole of B2O3. So once you divide this by half, this also becomes half and this also becomes half, okay. No need to reverse or anything, because this is our product and this is our product as well. So then that was our final equation right here. The delta H has to be 17.5 over here, which is then divided by 2. Okay, now what we're going to do is cancel everything out. Yeah, I pressed the button a little too soon, but anyhow, we're going to cancel everything out that we do not need, okay, in here. So HbO2 over here, the 2 moles of this is going to cross out with the one on the left hand side here. Remember, products, reactants. Okay, that's what you're canceling out. Product, you're going to add up. Okay. So then we go ahead and cancel out the half H2BO B4O7 here and here. That's gone. And hopefully we are remaining with the right amount of substances. We have a 2H3BO3 on the left hand side, which is over here. That's all that is remaining. On the right hand side, let's see what we have. We have two waters here, and we have half here and half here, okay, of water. So we are remaining with the 3H2O, which is exactly what we need over here. Okay, so this is our final equation. Then, so after doing this addition, you also add up all your delta H's, okay, together. So the manipulation that we did over here with the calculation, all you have to do now is add these up. Now remember, this is negative. So this is positive, positive, and then you add this one, which is negative, so you subtract it. Okay, really, so that's what you have to do. So Hess's law is really quite simple. All you have to do is manipulate the equations. Sometimes when you have 3 or 4 equations to manipulate, it's a little bit harder to work with. When you had 2 equations like we had in the previous example with the graphite, it's a lot easier to manipulate. Okay, but from me, you will definitely get about 2 to 3 equations to work with. I don't think I'll ever give you 4 equations to work with. But one way or another, with Hess's law, you should be able to cross things out. You should be able to get to your final answer. Okay, if you're not able to do that, then something is missing or you forgot to do something. But otherwise, it should always work out. And then we have something which is called the standard enthalpy of formation. The standard enthalpy of formation is a very standard condition, okay? And the standard condition means that it is taken under standard conditions where we have the standard atmospheric pressure, which is 1 atm, and the temperature is 25 degrees centigrade, which is not the standard temperature. Remember, that is actually 0 degrees Celsius. But in the standard enthalpies, then it is actually measured at 25 degrees Celsius. We will be talking about this again when we get to thermodynamics at the end of the semester. But for now, this is the standard enthalpy. Okay, and the standard enthalpy is indicated by a degree sign. So delta H, that is what we've been dealing with so far. So which means that when we measured the delta H so far, we really don't know what the pressure was of the system, and we don't know what the temperature was of the system. The temperature could have been 26 or 27 degrees centigrade depending on the day, and the pressure could have been 0.98 atmospheres or 0.8 atmosphere for all we know. So those temperatures and temperatures were not standard, but in delta H standard, it's going to be at this temperature and pressure. So we have to indicate that we have a standard enthalpy, and that is indicated by this little degree sign on the H. Okay, so delta H with the degree sign means that it is taken at standard conditions, and this is, it's a more accurate data. Let me just put it that way. Okay, and so um, that's how we indicate. And you can find the standard enthalpy of formation for everything, usually in data tables, because a lot of this data has been measured already. So even in your textbook, at the back of it, you'll find appendices. If you don't find those, then of course you can search online at NIST or Handbook of Chemistry and Physics. You will find all of this data, okay, in there. So the standard enthalpy of formation, for example, going from solid ice to liquid water, that is a standard, enthalpy. So you can find that. You can find Br2 liquid going to Br2 gas, bromine going from gas to liquid or liquid to gas. You'll find all of those standard enthalpies in data tables because all of this data has been acquired and it's recorded. Okay, and so when you have elements that exist in more than one physical state, then you have standard enthalpies of all of those. So for example, in the previous slides when we were working in the Hess's law, you saw that we wrote C graphite. We didn't just write C as carbon. Okay, we wrote C as graphite because C can also exist as diamond. Okay, C can also exist as Buckminster fullerene. So you can have 3 allotropes of carbon, so you really have to indicate exactly which allotrope you're talking about. All right, and so you have to indicate that. Some compounds have allotropes and not all of them have allotropes. Okay, and so you have to indicate which one it is. All right, and the standard enthalpy of formation delta HF, you will find this F here because that indicates that it's a formation thing. All right, so that's how the data is given to you. And the interesting thing about delta H formation is that delta H formation for an element in its reference state is considered to be 0. Okay, and what that means in the reference state is considered to be 0, meaning that things like oxygen, things like zinc, which exist, that is their elemental state. So if it's in their elemental state like that, then the delta H is going to be 0 for it. Okay, so any kind of an element just like that, all metals, sodium, potassium, copper, zinc, lead, just for those, okay, it's going to be 0. Bromine, iodine, hydrogen, H2, okay, all of these diatomic molecules, their value is going to be 0. Okay, all the other ones, they're going to have values. Okay, but in their elemental state, the delta H formation is 0. Okay, so here is an example of formation of water. And so if you see over here, the equation is pretty balanced. Okay, and the way the equation is balanced is in a fraction state. Okay, it's not in the other way. Okay, where you have coefficients where you have 2 moles or something. But here you can balance these equations in half also. Okay, and that's something very unique about thermochemistry. But anyhow, the delta H formation for the formation of water is this. Okay, which is negative 285.8 kilojoules. So the way we find this number, okay, over here, using the standard enthalpy of formation is using this equation. It's a very neat kind of an equation. It's also a very, very easy equation, okay, to work with. The only thing is that you need a whole bunch of data tables, okay, in order to find this. So delta H reaction would be, this is, remember, this big epsilon over here, this is the sum, okay? So this is the sum of products, and this is the sum of the reactants. So sum of the products and the delta H formation, and this is N. N is the number of moles. So for example, this is 1 mole, this is half a mole, and then this is 1 mole. All right, so in case for this kind of a reaction, the product would be 1 mole of water. So in our data table, we would look for here for N, it would be 1, and delta H formation, we would look for delta H formation for water. Okay, that's what we would look for, and then we will subtract the reactants from it. And in case of the reactants, now we will have actually 2 reactants because we have the water and we also have oxygen. Okay, now remember, both hydrogen and oxygen, they're both in their elemental state, so which means essentially the delta HF is going to be 0 no matter what your N is. It doesn't matter. Once you multiply it by 0, everything is 0. And so here the delta H formation, this number would turn out to be 0, which means that whatever the delta H formation of water is, that is what your answer is going to be. Okay, but essentially if these were not in their elemental state, what you would do is you will take the N multiplied by the delta H formation for hydrogen and then add the N, which is for oxygen, and then find the delta H for oxygen and add those two numbers together. That is what the sum is for. Okay, so we'll do an example, but anyhow, that's what the standard enthalpy of formation is. So here's an example of calculating this in a little bit more professional manner. So if you have this reaction given to you where you have methanol liquid going to methanol gas, then find the enthalpy for this reaction. Okay, and so then you find the delta H formation values for both of the compounds, and then you subtract the products from the reactants. Okay, that's kind of what we'll do. So delta H formation for methanol is this. For gaseous methanol, it is 200.7 kilojoules per mole. And remember these things, the only way you can find them out is from the data tables. There is no other way to do this. Okay, and so don't even memorize this. Don't look anywhere else. If I have to give you these problems, I have to give you the data tables. There's no other way to do this. So then you subtract the products from the reaction. The gaseous methanol is the product, so product minus the reactant, that's what you do, and boom, that's your answer. Okay, so subtract the two and you get up the answer, which is 38 kilojoules. Okay, so it's a very straightforward thing. Again, here is your product, 1 mole, okay, of 200 times the 200.7, and then 1 mole of the reactant, okay, over here. Nothing much to it. Here's another example for the standard enthalpy. And so here is the reaction given to us, and we are asked to calculate the delta H for the following reactions. 2 methanol plus 1 oxygen to give 2 formaldehyde plus 2 water. Okay, this is what's given to us, and the standard enthalpies are given to us as well. Okay, so see what is missing from here? Yes, figure it out. Oxygen. And the reason oxygen is missing from here is because oxygen is going to be 0. It is in its elemental state. Okay, and so oxygen is missing, no problem, no need to panic. So here we are. This is our equation that we're going to use with the products minus the reactants. The product is formaldehyde and water, and our reactant is methanol. All of these are 2 moles. Okay, so our setup is like this. So here we have 2 moles formaldehyde, which is 150.2, plus the 2 moles of water, okay, that we have, which is 285. So this is your reactants minus excuse me, that's the products. So minus the reactants, okay, which is going to be the methanol, and methanol is 245 right here, and that is 2 moles, so you multiply it by 2, and this is given there so that you understand that oxygen is 0, but it's not given here already anyway. So even if you don't add it here, it doesn't really matter. But anyhow, and this, I would suggest you use the square brackets so that you know that this is the product side and this is the reactant side. You can differentiate them. So you go ahead and you do the calculation, and then you subtract the two numbers, and you will get your beautiful answer. This is given step by step to you, and the answer is minus 380.2 kilojoules. Really very simple calculations. There is not much to it, provided you multiply with the number of moles and you do the calculation as in product minus reactants. Okay, so you have to take care of the signs. Okay, be careful of the signs, whether it's negative or positive. Other than that, it's very, very simple calculation. So where do we actually use thermochemistry? Okay, now thermochemistry, as I said to you in class also, is that it's a introduction to thermodynamics, which is a bigger picture for thermochemistry. So it's kind of a leeway to it. However, by itself also, it has a lot of applications. Okay, and one of it is of course in foods. Okay, we figure out how much energy is in food by using calorimetry and all that. So all the food calories that you see on the food packet, that is all determined by calorimeter. Okay, and so you figure out each of the processes that works, and then you figure out how much energy is being released when you burn glucose versus fructose versus fat or protein, whatever it is, and then you figure out how much energy is being given off. And remember, this is a very, very important aspect as far as biochemistry is concerned and as far as our body is concerned. And of course, considering how much energy is in carbohydrates versus fats versus proteins, it really helps to control how much you're eating and what you're eating. Okay, and everybody says a calorie is a calorie is a calorie, and that is really not true. Calories coming from carbohydrates are used in a very different way than calories coming from a fat. Okay, and so sometimes they're really not equal. Okay, and so the applications in food are unbelievable, because all food source for us is actually a source of energy. Okay, so um, this is one aspect, okay, of delta H, okay, where you have the heat of formation or heat of reaction, okay, for food. The other aspect, which is not covered here at all, is what happens to it when it goes into the body, okay, because not only are you burning food, you have all these processes that's going on in the body where energy is being used, okay, and so for breathing, okay, for your enzymes to function, you need all of this energy. So how is all that used up? That is all thermodynamics. So once you get to biochemistry, hopefully you will do that a little bit more. The second application that I can mention to you, of course, is fuel. Okay, that was previously, that was food was a source of fuel for our body, and now this fuel is for our life. Okay, as in life, as in our way of life, our cars, our homes, all of those. Okay, so fuels, which is the petrol or any other source of energy like natural gas, okay, all of those, that's fuel. So how much energy are we getting from each of those different sources. Okay, and how does all of that burn? Does coal give us more energy, or does natural gas give us more energy? What is it that gives us more energy, and which one is more efficient? That is kind of all where applications in fuels is concerned. So yeah, thermochemistry definitely a very important chapter, and then eventually thermodynamics is a very important concept and very important fundamental for our life. Okay, there's no getting out of thermodynamics. So anyhow, those two are some of the most important aspects of thermochemistry. So what I would like you to know from all of this that we've done so far, I want you to be able to do some calculations in calorimetry, definitely Hess's law, and of course calculations in the standard enthalpy of formation. Again, remember, for Hess's law, I have to give you all the equations. For standard enthalpy, I have to give you all the heats of formation. With the heats of reaction in calorimetry, I have to give you the data. Okay, that's all. So you have to manipulate the equations. I will give you the equations. Okay, in the exam also, I don't mind. I'll give you the equation. You have to manipulate them, and then you have to figure out the answer. Okay, all right.